Hi, g'day. In this video we're going to be covering what I hate teaching this because it's just not intuitive, but anyway, it's about other forms of acceleration. It's an important part of the course, and they're difficult to do, I think. They're difficult to figure out, but once you've got it, then you're pretty happy and you can just go forward. And these are the sort of the guidelines I've got here on the screen as to what to do. So if you've got basically we're trying to, if you've got an acceleration and we want to get v in terms of x or x in terms of a, like something strange, then what we want to do is just follow this guide to, instead of having a in our equation, to replace it with something else. So if a is a function of t, then we've done this before. This is the sort of the last questions that we were doing in the last videos. Then a is equal to dv dt, we know that, or d squared x on dt squared. We know those already. That's that one we've done before. This one down here, if a is a function of v, this is in the very last video that we did, and you've got initial conditions in terms of t and v, then just a is the change in velocity on time, dv dt. So that one is fine. These are the ones that we're talking about today. If a is a function of v, but your initial conditions are in terms of x and v, then this is the form of acceleration to use to undo all of the stuff that you'll see what happens. And if a is a function of x, then use acceleration is equal to the derivative of half v squared. So they're the guidelines. I'll show you why they work with some examples. So let's have a look at an example now. So here we go. An object travels such that its acceleration is equal to 3 plus its velocity. Its velocity at the origin is 1 meters per second. Find x in terms of v. Okay. So what we've got here, we've got a as a function of v. So we've got colour. A is equal to 3 plus v. A is a function of v, and also we've got an initial condition that its velocity equals 1 when it's at the origin. In other words, x is equal to 0. So what we've got, a is a function of v, and we've got v and x as our initial condition. So I've got v and x up here. This is the form that you should use here. A equals v dv dx. So what we want to do is change a to v dv dx is equal to 3 plus v. And you'll see that this looks good because we've got v's and x's. Okay, the entire thing is just v's and x's, which is nice. If we solve this, we'll get something, an x in terms of v. We'll get some sort of equation. That's what we're trying to do here. Okay, so let's give this a go. Let's see what happens. Okay, and so let's rearrange this. So dv dx is equal to, move v onto this side, so 3 plus v over v. And then we can solve this. Therefore, flip it upside down. X equals the integral of v over 3 plus v and dv. And if we sort of move this around a bit, we'll make that v plus 3 minus 3 there. What you'll get v plus 3 over 3 plus v, so that's just 1 minus 3 over 3 plus v dv, like that. Okay, so that's just a little trick to be able to get rid of v's and stuff like that. If you missed that, replay that, or ask me in class. Okay, now let's integrate that. That's v minus 3 log e 3 plus v, okay, and plus c. Okay, so that's x. X is equal to that. Okay, we're almost there. Find x in terms of v. All we need to do is use our initial condition. Velocity is 1 when x is equal to 0. So therefore, 0 is equal to 1 minus 3 log e. 3 plus v is 4 plus c. So therefore, c is equal to this awful thing, 3 log e 4 minus 1. So therefore, our function x is equal to v minus 3 log e modulus 3 plus v plus c. So plus 3 log e 4 minus 1. There is your function. Okay, so you can sort of see why it works, and it might be more intuitive to you, but they can get a little confusing. I've developed those guidelines to work. I've never found those guidelines never to work. So let's just have another look at one. An object is moving in a straight line. The acceleration is defined as this. Okay, acceleration defined as that. X is the position, etc. What we want to do is find a relation, find v in terms of x again. Okay, v in terms of x, and that's the little giveaway. V in terms of x, that generally means that a is a function of x, v in terms of x. You can just look at your guidelines here, your initial conditions, v in terms of x, and you've got a as a function of x. A as a function of x, we want to use this particular form of acceleration here. D dx half v squared. Okay, so we have a equals d dx half v squared. That's what we're going to use to be able to bust this guy out of jail. Okay, we're going to crack him out. So here we go. Let's rearrange and let's do this. Oh, probably need an initial condition too, don't we? Let's give it an initial condition. Let's just say x equals 0. We'll say v equals 0 when x equals 0. Let's just be really boring to do that because I'm running out of time. Here we go. So therefore, we've got d dx half v squared is equal to negative root x. Okay, let's deal with this one piece at a time. How do we get rid of this d dx? We integrate both sides. So let's integrate this side. We get half v squared. And let's integrate this side. That's the integral of negative x to the half. Okay, dx. Therefore, half v squared equals, integrate that, so that half goes up to 3 on 2. 3 over 2, and then we divide by 3 on 2, so that's negative 2/3 x to there plus c. Okay, let's now substitute v equals when x equals, and so we'll substitute that into there. So therefore, we've got 0 equals 0 plus c. Therefore, c equals 0. Very interesting. Let's show some boring numbers. Therefore, I've got half v squared equals negative 2/3 x to the 3 over 2, and I just solve for v. So times that by 2, so v squared is equal to negative 4/3 x 3 over 2. Therefore, v equals plus or minus square root of negative 4/3 x to the 3 over 2. And there's your answer there. That's the velocity function in terms of x. So follow these guidelines. I've never known them to steer you wrong. Look at your initial conditions, look at whether a is a function of x or v or whatever, and just follow those and follow your nose. Enjoy.